electrical field, differential equation of electrical field, which I wrote in the following way: divergence E equal delta over epsilon naught. First of all, its differential equation. I will speak about the physical meaning of why of this equation again and why we deal with differential equations. But what is the most important, in order not to lose track, we derived this equation, we didn't do it here, but we derived it from Coulomb's law, nothing else. Coulomb's law was used. Let me do it again because it's important. I use Coulomb's law, but I didn't tell you how to do it in order to save our time. I derive this equation: flux through closed surface equal charges inside divide epsilon naught. And then from this equation, the differential equation of electrical field. So all information about Coulomb's law here. If this equation is wrong, it means wrong what? Coulomb's law. I don't advise to argue with Coulomb's law. So it's another painting of the picture, another language. Either we know, if we accept Coulomb's law, we don't have choice, we have to accept these two equations. They were derived only from Coulomb's law. Clear? I will return. So we derived two forms. Now, let us speak a little about this equation. We need to speak. I like to say, gentlemen must pay. I don't know how to say about girls in this respect, but gentlemen must pay. Somewhere he win, somewhere he lose. That's a rule of life, a rule of our work. This equation always is correct. This equation, it was derived from Coulomb's law. This equation is not always correct if we consider divergence as sum of derivatives. Derivatives have meaning when function is continuous. If it's not continuous, this equation does not have meaning. So this equation is always valid inside of layers, inside of our body, inside of borehole, above of Earth, but not at interfaces. Why? Because I told you, even at the beginning, in the first lecture, there is one stupid component, which is very clever at the same time, normal component electrical field, which is discontinuous. Because it has jump always, at any interface, as soon as there are surface charges. So, third form of this equation is difference of normal component is equal, as I wrote you at the beginning, density of charge, divide some constant. Three forms of the same fact. What is the same fact? This is device which tells, do you have charges inside? This is device which tells you, at this point, do you have density of charges? This device tells you, do you have at interface surface charge or not? If, for example, there is no at some point surface charge, it happens, then normal components from both sides are the same. What I wrote here, normal component above, normal component beneath. Clear? Everybody understands? Three brothers, which contains the same information. This equation is always correct at so-called regular points, but we don't engineers to think about regular. Simply, inside of layers, inside of our body, inside of borehole, but don't touch interface. At interface, instead of this equation, we use here. Why? Because this term one of these terms contains derivative from normal component. If normal component is different, what happens with derivative? Huh? Suppose I have different values of from one side 1 millivolt per meter, from another 0.5 millivolt per meter. Let me plot graph. What happens derivative at this point? Huh? Sorry?
Not stable.
Not? How could you interpret?
You start to get infinite.
Oh, it's equal infinite. Or it's simply equal. In order to take derivative, let us not go in detail. I have to take derivative. It's not too bad to know what we are doing when we are taking derivative. I have function. I don't care what is the value of the function. What I have to do, take value from one side, take value from another side, take difference, divide by what? Huh? With the small displacement. So, if function discontinues here, what would happen? Difference in numerator, delta y divide delta x. Difference finite, but denominator goes to 0. We are not talking about left, right derivative, so it's not defined. So that's the reason why instead of this equation, which is always valid inside, we are forced to use this. It's called surface analogy of this equation. We don't do anything special. We are authors of story. We describe how field behaves. That's all. Where is how it behaves? Inside of layer, at interface, 3 forms. Now, but this all 3 equations has one feature. Very, very important feature. They tell a relationship between source charges and field, which, not from high theoretical point of view, which from common sense. This equation is extremely natural. They tell you relation again between parents and children. Electrical field is caused by charges. Charges are parents. This relation tells you at each point what is the relationship between what created and result, between cause and result, correct? That's the meaning of the flux, that's the closed surface divergence, and this last condition. I told you half story. So what I'm doing, I replace very complicated course of theory of vector theory of the fields by my ability to tell you waving my arms. So, by using my fingers. Now, I told you last century 2 tools were developed. What is so? First tool is flux through closed surface or divergence. That's the same. It was invented second tool. And before I'm going to tell you about second tool, let me add a little, even I'm in trouble with time. Let me show you, you will see how many fundamental facts are very simple. Tell me please, I have a volume, I have charges here. What divergence electrical field shows? Now help me at this point. Now I need your help. Let me take small volume, delta V. That's volume V. What divergence shows at vicinity of this point? Density of charges, correct? Now, if I multiply by volume, small volume, what we will get? Charge, not charge, charge. Charge where? In this volume. Density times volume is charge. Now, I mentally perform summation over all volumes. What it will give me? Total charge inside volume, correct? Do I know another tool which also gives me total charge? Flux through flux. through closed surface S over electrical field. Who knows how this relation is called? Gauss theorem. There are only two theorems in all theory of geophysics and mathematics, Gauss and Stokes. But let me, to discuss this, that's, you see, we didn't perform one derivation. We only looked at the essence of each quantity. And we got 50% of all theory of the inverse problems. Watch about importance of this Gauss theorem. By the way, it's true for seismic, it's true for gravity, magnetic, electrical, everything. Hydrogeology, hydrodynamics, etc., etc. Let us look from geophysical point of view. It's a bridge. It's amazing bridge between what and what? Field where? On the surface. And field where? Inside. So let me now look as geophysicist in this matter. I have Earth surface. I have my target. What this equation tells me? It tells me if I know electrical field on the Earth surface, I don't speak accurately, especially. It's not theoretical course. So if I know field on this surface, at this point, that's my surface, correct? Which surrounds my volume, Earth. All of you see it, huh? That surface S. And also there is very huge surface where there is no any field. So suppose I perform profiling, measure field here. Theoretically, I have information about what according to this relation? About sources or field where? Inside. That's field on the surface. That's integral where? On the surface? No, beneath. This equation is the basis of all interpretation algorithms, whether we say or not, which are used in magnetics, gravity, electrical, and acoustics, or when we use longitude P waves. That's a relation. From this relation, all green formals, all method migration, Kirchhoff's, all comes from here. But how simple. For us, don't go in details, but understand idea, concept. Because here and here, total amount of sources. Now, back to, that's all about divergence. I will not tell anything else because we have to speak about frequency responses, time responses, etc., etc. Now, geological noise, we will come, only patient. Now, last century, second tool was invented. One tool, you remember, flux through closed surface of any field. It shows amount of sources. What is the second tool? Who can extrapolate what I did? What is the second tool? In no more tools. No more. All textbooks about theory are based on these two tools. Only different shape, different face. Huh? Before curl. Because I didn't introduce at the beginning curl. I introduced what? Flux through closed surface. So mathematician found out. Flux through closed surface gives total amount, for instance, sources, some constant, doesn't matter. Depends on system of units. Now mathematician invented second tool. What is the second tool? Guess. I need only, if you don't know, I will not make suffering here too long. So they found out, if you consider integral not over surface, much simply, along any closed contour, any shape. Integral MGL. It looks like, what is the deal? Integral along the path, divide many elements, take field, dot product, again dot product, perform summation. It's a pure mathematics. What is the interest? Go to computer, calculate, that's it. But as flux through closed surface, this integral has fantastical feature. Its second litmus test, its second device. And what is the device? It tells you how many generators of second type going through any surface surrounding by this contour. Is it clear picture? I'm not good painter. Just a second. So contour L. If you take integral from field along this contour, procedure is very simple. Divide many elements, take dot product, perform summation, and this integral is not simply number, it's a scalar, of course, as previous. But it has a power. It tells you whether you have vortexes or generators of second type which are going through this surface. And this integral does not tell anything else. It's not abstract number. It's device. Flux through closed surface, it's device, which tells you amount of sources. This integral tells you amount of vortexes. Let me give you example. Because vortex is not pleasant word, it always creates some confusion. Now, that's current. You don't need that wire. Please imagine, that's normal current with which you are faced, especially those who are working in mineral exploration. So current, charges are moving. Clear? That's not source. That's called vortex. This current is the classical example of generator of second type. Source is a scalar, number. But current is something else. It has not only magnitude, but it has also direction. So it's a direction. So that's called vortex. So what these great people, first of all Stokes, in first case Gauss, Stokes, discovered for all fields, not for only magnetic, electrical. If you take contour, can you imagine contour? But that's a contour, you see? Contour. If you take integral from, just a second, that's it. From, that's current, and then I take contour from magnetic field B, BGL. We will come back to this. Understandable? Do we have magnetic field at this room at this moment? By the way. Huh? What is the magnitude of constant magnetic field at this room? Theory, but practice is practice. So, what is the value of constant magnetic field at this point? Approximately. You can make error 20%, I will accept, because I don't know. Huh? 50? 50? 55? Of what? Thousands of what? Nanotesla. How we call nanotesla in different little way? Gamma. So that's lovely magnetic field which we have here. Correct? Now, there are it's normal magnetic field of the Earth, but also there are a lot of wires. In Saturn there is another magnetic field. Now, what is interesting? If we are talking about, first of all, constant magnetic field. If you take integral from magnetic field around this contour, what would be the value of integral? According to general theory, it tells you about amount of currents which go through surface surrounding this contour. How many currents going here? None. So this integral is equal 0. You see how nice. Now, let us be brave. Let us back to electrical field, constant electrical field. What creates electrical field? Charges. No vortexes. So take integral along closed path from electrical field. What would be the integral? 0. You don't care what is the contour. You can imagine many layers, many boundaries, therefore bodies, borehole. Take arbitrary contour. And theory tells, I don't care what is the electrical field, what is the contour, but this integral has one feature. It tells you, are there vortexes or no vortexes? But Coulomb's law tells, sorry, only charges create electrical field. Therefore, this integral must be equal 0. That's second powerful tool. Now, in order to kill this tool and misunderstand, let me take contour around this current. Arbitrary contour. Very complicated shape. No way to find mathematical expression for this contour. Many complicated parts. What would be the value of integral along magnetic field along this path? It will be equal, no, that's current. It will be equal value of the current which is going through this wire. Because this integral has one quality. It tells you how many vortexes. Current is the vortex of magnetic field. Clear? Now let me change contour. I will take this contour. What will value of integral? Current. Let me take bigger current. Now let me make stupid things. Let me start to change position of the contour in the space. Clear? If I start to rotate this contour, what happens with the value of the integral? It still will give me current. But then I make completely stupid things. I take contour in this plane. Understandable what is the contour? It's located in the plane in such way that current tangential. What would be the value of integral? 0. Aha. Mathematicians realized this fact. And they wanted to avoid this unpleasant situation. They wanted to take such contour that it would be which would show always magnitude and direction of current, for example, or vortex. Doesn't matter what is the vortex. And then they decided, if I have many different, for example, current, let me take contour very small, which is located in the plane perpendicular to the current. Clear? Then, in direction perpendicular to this current will be direction of my vortexes, correct? That's my contour L, that's my current J. So, they decided, let me take, for example, for magnetic field, this contour and divide by surface. Without surface, what this integral shows? Total current which going through this contour. Now if I divide by surface, what I will get? Current density. So density of the vortexes. And this quantity is called, it's time to tell you, curve. So you see complete analogy with previous case. What I'm telling is true not only for magnetic field, for all cases. So integral MDL along closed paths proportional number of vortexes. Now, if you take small contour, so small that vortexes distributed uniformly, you remember masses distributed uniformly. Therefore, if contour is small and divide by area, it will give you density. But since you took area perpendicular to vortexes, multiply by unit vector n, but that's our surfaces, vector n, and this quantity has name curl of the field. So curl, unlike divergence, is vector, which shows density and direction of vortexes. There are three types of vortexes. We will speak about each of them. So let me summarize. And then we will go to electrical field back. That's preparation. Now we will make mathematicians proved circulation along closed path gives you number of vortexes or number of generators of second type. Nature does not know third type. Only sources and vortexes, that's it. Now, it gives you number of vortexes where? Which are going through surface surrounded by contour. Clear? Now, this integral does not tell you what. Where are these vortexes? Here, 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 here. You remember? The same story happens with flux. So, mathematician decided, very well, let me take small contour. Small. What does it mean, small? Such small that vortexes will be distributed uniformly. They are distributed uniformly, suppose in this way. Let me take contour not arbitrary, but in the plane perpendicular to vortexes. Let me divide this integral, divide this surface. That gives me what? Density of the vortexes. Let me multiply by unit vector n perpendicular this surface. That's all together called curl M. Complete analogy with flux. Two generators of the field, two equations. Now, let us, that's the meaning of the curl. We will see it several times. So when I ask what does curl mean, everybody wants to take finger and show circle. Does not have any relation. Curl, it's some translation rotation, no rotation at all. Simply you forget about finger, forget about rotation, simply curl is device, is the vector which tells do you have here vortexes, generators of second type, or you don't have. That's it. And I will show you when we start to consider Faraday's law in detail. What does Faraday, the curl mean? Now, let us apply our knowledge. Fortunately, we are leaving this subject because it's far away from geophysics, but it's useful to know. Otherwise, when you ask what does Maxwell equation mean, you can only by heart remember, but don't know what is it. Divergence, curl. Now I hope it's clear. Divergence and curl, two devices which show two types of generators of the field, any field. Clear? So let me write here. Now, just a second. Just a second. Let me write here Coulomb's law. We didn't use anything except Coulomb's law. From Coulomb's law, you should believe me, we proved flux of electrical field through closed surface equal charge divide epsilon naught. Then we developed another form equation, and we developed third form equation. Now, I would like to find circulation of electrical field along closed path. Tell me, please, according to Coulomb's law, what is the value of this integral? No derivation, only thinking. Zero, because Coulomb's law tells you only what creates electrical field? Charges. So no vortexes. So therefore you have to write zero, always, without any exception. You see how nice to understand meaning, and then you can write instantly very important fact. Then, what is the curl electrical field? Again, I don't care what is the expression up to now. Curl, density of the vortexes. Believe me, if no vortexes, no density of the vortexes. So, zero. Now, mathematician didn't like integration. Again, you see how I repeat, nothing new. So they wanted very much to express curl not as ratio integral over surface, but through derivatives. And they found curl is expressed through derivatives. So again, it's good when where? Between interfaces, at interface. It turns out, using this equation, it's simple matter to show tangential component electrical field. Just a second. That's interface between any medium, any formation. From this equation it follows, if you consider tangential component electrical field from one side medium, another side, what would be difference between them? What do you think? Zero. If it's not zero, therefore integral along any closed path will be not zero. Therefore Coulomb's law would be wrong. I don't advise you to think this way. So let us take seawater and bottom, very conductive medium in seawater. Let us look carefully. Let us try to measure voltage between these 2 points and between these 2 points. What is your these two pair of points located very close to boundary? Here is seawater. Here resistive, high resistive bottom. What do you think? What would be difference between voltages? Or electrical field, if you don't like voltages? Nothing, the same. Iron rule, electromagnetics, it turns out it's not only true for constant electric field, always it's true, always. At interfaces, electrical field from both sides is the tangential component of electrical field is the same. You don't know fields. For example, you are working or body. You don't know resistivities. You don't know shape. But always for direct, it turns out, not only direct alternating fields, tangential components, electrical field are the same. Tangential. What about normal? Oh, I'm sorry here. Normal defined by density, tangential, always the same. That's iron rule. So let me write down these three forms. Curl electrical field is equal 0, and difference tangential component at interface is 0. I derived 3 forms of so-called first equation of electrical field. All of them came from Coulomb's law. Let me speak about this equation a little. And then we will summarize. We are very close to system of equations. I have a loop, current loop. Not current loop, I'm sorry, receiver loop and voltmeter. Clear? Voltmeter and loop. Now I decided to do the following. A electrode, B, and why I have to put my Mn receiver electrodes? It takes time. I would like to get rid of receiver electrode M and N. And using immensely rich experience of electromagnetic methods, instead of receiver electrodes M and N, to use loop. Can I do it or not? You understand what I would like to do, or you lost? Lost? Huh? Lost? Everybody saw 4 electrode array in electrical methods. I mean mainly for students. I don't want to offend engineers now. I mean students. So you are in the field. You took current electrode A and B, created electrical field. Now, why we have to use another receiver electrodes Mn? Let us take loop, nice loop, 1000 turns, or 1 turn as you wish, connect with voltmeter, and without grounding to measure what? Just a second. Let me do the following. Your silence is dangerous for me. So, Earth surface, I have current electrode, one another. Battery, ampermeter. Do we have electrical field due to these electrodes in the Earth? Now, do we have electrical field at this point? Do we have electrical field at this point? We have everywhere. Correct? Now I would like to measure this electrical field. So, instead of electrodes M and N, I again do the following. I take wire, put on the ground to loop, and connect with voltmeter. There is at this point electrical field. All of you understand? I put wire, real wire, insulated wire on the ground, and connect, loop, closed loop, closed. Even I twist these wires in order you would not see gap, distance between them. Now, there is electrical field at this point. There is electrical field at this point. What voltmeter measures? Huh? What it has to measure? Only don't tell me about potential. I don't know anything about as voltmeter. It measures, it's called voltmeter. Again, it measures voltage. What voltage by definition? Let us call point M and N. Voltage between point M and equal integral. At this point, there is electrical field. There is at this point electrical field. There is. So I have to take integral electrical field times dl. True? So it's a great, almost Nobel Prize. You don't need to put receiver electrodes. You can use loop. But what you will measure? Zero, nothing. Why? Because circulation of electrical field shows what? Number of vortexes. But electrical field does not have them. So voltmeter honestly will show you zero. That's only one reason why we don't use loop when we deal with constant electrical field. So it's not too bad to understand. Clear? And we are forced to put our M and N in measure voltage between two remote points. M and N. So what is the advantage of such approach? As soon as you understand meaning of equations, not formulas, not for shape, but essence, a lot becomes clear. Let me show you another things which follows from these equations. When integral along closed path equals 0, what do you think? We will not prove it. It's too simple, it's too known. If I have voltage, I have electrode M and electrode N. I put wire, please imagine Earth surface. Earth surface. That's voltmeter. What voltmeter measures? We have agreement already. Voltage between point M, N. M, N, E, DL. Again, let me repeat. That's what voltmeter indicates. You have electrical, voltmeter mentally divides wire in many pieces. Take dot product electrical field times length of the wire, angle, perform summation, that's voltmeter gives you. Now, you came to the point of observation. For not students, for those who worked in the field, do you care how you will put wire between electrodes M and N? Huh? Really not. Without knowing why, by the way. But always you came to the field, put short wire, or sometimes long soundings, DC. You put wire on the ground, connect one point of wire with electrode M, another with electrode N, and you measure voltage. I don't know one operator who would ask himself how I put this wire. It laid down on the ground, and that's it. Why it happens? Why? It's always true? No. But this equation tells us what? Who knows? Sorry? Overloop. That's overloops integral equals 0. But from here, this fact follows from another fundamental fact. Electrical field is not caused by vortexes, only charges. But from this fact follows another fundamental fact. What is it? Voltage is independent on path. Do you think it's obvious? No. That's true only for electrical field. For something else, which I after 1 minute tell you. So that's the reason, without even never it's written instruction. As soon as your electrode Mn are fixed, you don't care what is the wire, how it's located. But don't think, it's not obvious. It's amazing fact. It's paradox. As soon as you understand what does voltage mean. Voltage mean, that's what written here. Divide wire many elements, take dot product, perform summation, that's voltage. It's again amazing device, voltmeter. That's what voltmeter is doing. When you measure, you think it simply measures. No, it divides, not literally, divides wire in many elements, take dot product, perform summation, that's voltage. It's not so obvious. Now, if it's not so obvious function, it's not clear why changing position of the wire result remains the same. Because here electrical field different from this electrical field, and length is different. But due to the fact there is no vortexes, you can bravely say, I am not worried how I put wire. Let me give you another example from gravity in order to increase your understanding of importance of insight of our physical laws. Gravity. Take these 2 points. There is gravitational field at each point. Can I take integral j dl between 2 points A and B? Can we do it? Can we take gravimeter, microgravimeter, and measure at different points of this path? Well, that's the path. Let us take length, multiply by, even let us, since vertical component, let us take this path. That's better. Here I measure gravitational field, take length 10 centimeters, here, I calculated integral, correct? Now I'm doing the folding. That's real distance between these 2 points. Now I take next contour from this point to Sydney. Is it longer a little than this part? Yes. But that's not the end of our suffering. Then I go to the ocean. My path goes to the ocean to North America. I arrive to Los Angeles. Then I go to Red Rock. Mountains, high density of the rocks. Then, finally, through South America, I will return to this point. Is the difference between distance here and second path? Very small. Let us mentally again calculate this integral. Gravitational field through mountains at each point times length. You follow me? It will be so that's one path from M to N, and then from M to N another path. Can you tell me these integrals will be the same or not? What your intuition tells you. Why do you know it? Why? It's not obvious. Don't accept quickly what is not obvious. Why? You are right completely. But it's a miracle. And real knowledge comes when we pay attention miracles. How you can be brave, say, so long path, completely different than this path. Gravitational point at each point, gravitational field will be completely different. It's amazing to think after summation, you have to get the same result. Why? Because gravitational field is caused by only mass sources. Therefore, integral from M and this way or any other crazy way must be the same. Only in this case, integral along closed path will be 0. So if you know there is no any field in P waves, not shear waves, P waves, in electrical, in gravity, path, voltage, we can use that voltage, JDL or EDL, always along closed path, 0. You still don't have questions? It's strange. Now, so what we did, how many minutes we have if you're not tired? Huh? Few moments. Okay, very good. Now, so we are going through difficult part. Very soon we will finish completely with this stuff. Next hour. We derived 2 equations of electrical field from Coulomb's law. Curl electrical field equal 0. Divergence electrical field equal delta over epsilon naught. These 2 equations form system of equations of electrical field at regular points. At interfaces, always, without any exception, difference of normal components equal density of charge, and tangential components, electrical field, are the same. Everything is derived from Coulomb's law. What this equation tells us, source vortexes electrical field are absent. What is written here, sources of electrical field are charges. Now, instead of, since we have to finish now, you have to rest, I would like to ask you one question. We have to approach Maxwell equations. How many equations in Maxwell system? 3? Okay, 3. Okay. What are there? There are usually 4. Watch. Electrical field 1. How many equations describe electrical field? 2. 1 divergence, 1 curl. Why there are here? Again, I repeat, because it's the most natural way relationship between field and what? Generators which create it. So very soon we will see Maxwell equation, not tomorrow I think, when you see 4 equations. Why? Because 2 fields, electrical and magnetic. So everything becomes reasonably logical. Let us stop here now, and then we will go away from Canada. He's still very good. Now, just a second. We are going through most non-geophysical part, but engineer, I believe, I am an engineer, I'm not a mathematician. I never told about myself from another. I didn't tell you at all about myself. So I'm not physicist, I'm not mathematician. I graduated many years ago from Moscow Institute of Geological Prospecting. I'm pure geophysicist who mainly worked in mineral, developing methods for mineral, from logging, from surface oil exploration, but I used only mathematics in order to solve our lovely, I used that chance that you left, tell about myself. So I look at this equation only from geophysical point of view. If you start to ask me to prove some theorems, I don't remember that I once proved one theorem of my life. No way. My way of thinking completely alien to this type. So let us, as most of you, I have a diploma in mining engineering geophysics, and I'm very proud of it. Now, but I do believe each engineer must understand in order not to look as technician. Now, what I did, I derived system of equations of electrical field. These 2 equations are valid inside of layers. These 2 equations are valid at interfaces. They contain the same information as Coulomb's law. No more, no less. But only differential equations. Why differential equations? Because here derivatives. Why we did it? Why we need it? Remember, we failed with Coulomb's law to solve the forward problem. We failed. So in order to try to avoid it, this system was derived. And you will see a little later, after physical consideration, I will return back to mathematical part, I will show you these two equations do allow, together with some additional information, to solve the forward problems. So it's done for practical purposes. Now, why without going in detail, why differential equation allows us to find field? In mathematics, in applied mathematics, differential equations are very widely used. Let me tell you something, only which will be some glue, concept, explanation of concept. If I write you equation, can you tell me about this function? I hope I wrote correctly. dy dx equal constant. I know, I don't know function, but I do know equation which describes this function. You follow me? I don't know function. I would like to find it. But I do know, for some reasons, my unknown function satisfies this equation. Who can tell me what is the function? Huh? Linear function, you see? So it's not very wild, unusual way to proceed from differential equation in order to get information about function. Yx equal cx plus c1, who knows? Correct? Now, so let us develop way of thinking. You have equation, and very often you can say what is the function. That's behind of all this operation. Let me do a little more. I have function, equation, which describes function which satisfies this equation. A little more complicated equation. Do you know function which many functions which satisfy this equation? Do you know? A little more complicated, longer silence. Sorry? We will check now. No. What is the function which, let me help you. I will write only 3 equations. One I wrote, second I wrote, I will write third equation. One, two, three. Completely different equations, correct? Pay attention sign, also it's important. Do you know solution of this equation? Shame. So, since I'm old, I can tell you shame for me, youngest. It's equation which describes so many important phenomena. Just second or first? Last? Exponential. Let us check. Please substitute here. What would happen? Huh? Sorry? 3? That's better. Trigonometrical function. Yes, that's what I had to. Okay. So this equation, if you substitute this function plus minus, it will satisfy this equation, correct? Take first derivative, take second derivative. You will see they are equal. Thank you very much for information. How we call this equation? Solution of this equation, sinus mx and cosine mx with some coefficients. What kind of phenomena that describes this equation. Harmonic oscillator. Take, for instance, spring with mass. Move it. That's solution of this equation. You will see sinusoidal oscillation. By the way, what is the m squared? It has even physical meaning. M, not m. Frequency of free oscillations. It tells you exactly how this mass will oscillate, or current in the circuit, which does not have resistance. So, I am not going to teach you differential equation. By no means, I don't know that in order to teach. But what I do know, when I look at equations, I can guess what is, many cases, solution. Clear? That's the idea. Exactly the same story here. When I look in the differential equations, if I solve them, it looks like I can find solution. That's the reason when mathematicians, physicists failed with Coulomb's law, you still remember why? Because we don't know what sources which arise. They were forced to go along different road. Real heroes go around, if you know, not straightforward. So that's the way how, based on experience in mathematics, when physical law is useless from point of solving forward problem, let us try differential equations. That's, we will come back it, I promise, not a lot, because the main part is done in this stage. So these equations are written in order to solve forward problem, remembering equations tell us about answer. If I write, for example, such equation, I hope more or less I am right. Do you know this equation? For sure you don't know, but it's a Bessel equation, one of the most famous equations in geophysics. Again, I see equation. I know what the answer. That's the goal of this system of equations. One more comment and get rid of equations. How many solutions this system has? Infinite. How many solutions this equation have? Infinite. Change constant. So it's good and bad. Good because all electrical constant electrical field which obeys Coulomb's law must satisfy this system. So it's a storage. This system is storage. We have to pick up only solution which corresponds our given problem. Let us stop here. One a little effort, and we will go to the second physical phenomenon of great importance. This, how many equations written here? How many? 4. Because it's a vector. It has 3 components, plus this vector. So it's a stupid system of 4 equations. So mathematicians decided to simplify life for us geophysicists. And they show if electrical field is caused by charges, sources, then it can be presented as what is it? Who remembers? For all, in P waves, seismic, in gravity, in electrical, even in magnetics outside of magnetic bodies, if curl equals 0, it can be presented as gradient of electrical field. Again, today I'm trying, before lunch, I will give you difficult part, but then will be easy. Again, common sense. We don't want to work with vectors. So maybe it's possible to simplify life and deal with this quantity. This quantity has a name. What is it? Potential of electrical field. So it was introduced only for one reason, to simplify. Now, what does it mean, for instance? It means any component of electrical field equal du dl. So, for example, if I have potential at this point, take difference, divide distance, you will get, with accuracy of sign, minus component of electrical field in this direction. You would like to know electrical field in this direction. Take electrical field at this point, take difference, divide distance, component electrical field in this direction. Now, tell me please, if I could add some constant, what happens? I have potential at some point U, at some point P. It's 1 millivolt. Then I add constant 10. What happens with component of electrical field? Nothing. Derivative from constant, 0. So infinite number of potentials satisfy the same electrical field. What I would like to say? Potential does not have any physical meaning. It's not electrical field. It's not real force. It's a mathematical tool. But it's very useful. So it turns out it has another beautiful application. You would like to calculate voltage between 2 points, E, G, just a second. You have 2 points, M, N, you have wire. You would like to know voltage between points E, G, L. Complicated story. You have to divide contour, many elements, take dot product. But potential allows to get rid of this problem. What is the expression for voltage? And some of you told me at the beginning. It's equal potential at point M minus point A. But I don't advise you to tell me that voltmeter knows about potential. It does not know at all. We introduced it. So voltmeter does not measure difference of potential. It measures voltage, what really has meaning. But physicists and mathematicians invented method which allows to represent voltage as difference to numbers. That's what we are doing in the field. We will use it without any doubts later, when I start to consider specific arrays. Now, when mathematicians introduced potential, they wanted to get rid of this system. So follow me. I started from Coulomb's law, replaced by these 2 equations. And now I would like to make next step in order to deal with scalar, with simple functions. Simple mathematics shows if we replace electrical field into this expression, we will get very famous equation. I doubt that you don't know it. This equation is, do you know what is it? How it's called? Poisson. Poisson equation. So you see, now we are almost accomplishing our long way of mathematical concept. We started from Coulomb's law, derived system of equations, and then we would like to make life simply. Instead of 2 equations, we obtain 1 equation, which is called Poisson equation. It's very widely used in theory of electrical methods. So it's stage number 3. Now let me stop here and go to the next subject. We too long spoke about mathematics. Now, what do you think? Let us go back to geology. Our rocks, the electrical, are they characterized by dielectrical features or no? They are dielectrics or no? Huh? Are there conductors? Is the contradiction between dielectrical and conductor? Is it possible? Water. Let us take water. Water is dielectric or conductor? Huh?
Depends if you're static or...
No, stop. We are talking about constant electrical field. Constant. But water, is the dielectric or conductor or both? Not dielectric. Huh?
Not with a constant electric field.
If you have constant electrical. But for example, we put our electrodes A and B into ground. So we finish with system equations, you understand it. Now we are going about, that was only preparation. Now again, I have earth, I put current electrode A and B. Is it dielectrical or conductor or both? Why it's not dielectric? Why it's not dielectric? If I ask you, what is the dielectrical constant of the water? What is it? 80. Relative. Because the electrical constant is epsilon R, epsilon naught. In practical system of units, it's a constant, 10 minus 9 farad per meter. Epsilon R for water is equal 81, or 80. What about oil or gas? What about clay? Well, let us take any type of oil. Heavy, light. What do you think? Order. Huh? Too much. So it turns out the electrical constant, relative electrical constant of the rocks changes between 1-2 units and 80. That's approximately. Now, of course, we don't have pure water, we don't have pure oil. We have mixture. When we don't have, for example, oil at all, the electrical constant clay 10, dolomite 20 relative units. So it's a very important parameter. But what does it show? Why we are talking about the electrical constant? Because when you create electrical field, something happens inside of molecules. What happens? You created current, there are molecules. So some of molecules are already deformed, and center of positive and negative charges are not the same place. Or due to electrical field, we observe deformation of molecules. So anyway, all these effects are called how? We don't need to go in detail, but how? It's called polarization. It's a very important phenomenon, polarization. We have two polarization. In one case, it's vital. Where is the method where polarization plays very important role? Huh? There is one geophysical method which is completely based on polarization of something else. No, that's electrical, but I'm asking about outside of electrical methods. Magnetics. There is a remnant, induced magnetization. Magnetization is another word of polarization. It's the same. Now, why I raise this question? There is a second phenomenon which takes place in the rocks. First phenomenon, we discuss electrostatic induction. Second phenomenon, polarization. Due to polarization, inside, when we have molecule which is not polarized, positive and negative charge at the same place, and there is a total amount is equal to 0. But when polarization takes place, there is a shift with each other, and it results in appearance so-called bounded charges. So there are two types of charges, free and bound charges. So there are free, delta equal density, plus bound charges. These charges do depend on the electrical constant. But in all electrical methods, we are awfully lucky. We know we are lucky. We never think about it. If you take all equations for electrical field, for Schlumberger profiling, for mining methods, logging, nobody takes into account bounded charges. But these charges do depend on the electrical constant. So I only wanted quickly to emphasize one fact. And in this respect, you are right. Only in this respect. When we have conducting medium, two parameters define behavior in general electrical field: conductivity and the electrical constant. But it turns out that these charges, even they appear in such way that their density together with density of free charges is independent on conductivity. It's again one of the miracles of electrical methods. So again, there are free charges, there are bounded. Free charges depend which depend conductivity. These charges depend conductivity and the electrical constant. But all together, in conducting medium, unlike static, in conducting medium, are distributed in such way the total charge becomes function of conductivity. That's the reason why in electrical methods we don't need to take into account. Otherwise, it's a very strange if you have some free time sitting in the field performing measurements. You have to think, wait a moment. Clay has one electrical constant, dolomite has another electrical constant. There is interface to media, not only with different conductivities, but also different electrical constant. But physics and theory shows everything happens in such clever way that sum of total charges is independent on the electrical constant. That's the reason. It's only a few minutes of talking about it. We are saved. Otherwise, in constant electrical methods, we would have to take into account both the electrical constant and conductivity. But we are simply lucky. And there is no way using constant electrical field to get information about the electrical constant. In this sense, we say they are only conductors. But in effect, everything is more complicated. 5 minutes about this subject. Third phenomenon, which I am going to discuss together with you. Ready? Conduction current. Third phenomenon, conduction current. We have conducting medium. Again, we are talking about our model of the Earth. We have electrode A, B, receiver M, N. Row 1, row 2, row 3, who knows? Let us define what we need later. At each, due to current electrode, current arises, correct? Current density, what is it? We will use it. What is it? Who can define it? What?
Charges in a specific area.
What is the specific area?
Whatever closed surface you might like to take.
Closed. So we know electrical field, correct? In conducting medium there is second field, current density field, field of current density J. So not too bad to remember what is it. It's amount of charges which are going per unit time, per unit area, per unit time, per unit area, when area is oriented how? That's, you see, three factors are vital. If you one of them you missed, no understanding. So when I write this vector, we will use an electromagnetic field everywhere. That's the reason why I'm preparing you. Current density, it's not simply vector J. My suggestion, visualize amount of charges. See it. See, tell you, aha, J equal such ampere per meter square. If it's equal 10, it means 10 charges, coulombs. Cross per unit time, 1 second. Unit area per unit time, and area is perpendicular. Now, second physical law. Ohms establish this law. It tells current density is equal what? Conductivity times what? Ohm's law. It's a very useful law, no doubt. No more curl, no more divergence. So let us go to physics. So what current density is equal what? Conductivity times the electrical field. Correct. So at each point, amount of charges which are going per unit time proportional electrical field. It's so natural. Because the strong electrical field, the more charges will go. The weak electrical field, less current amount of charges. And this physical law is called Ohm's law. Now, that's second physical law. We need 3. This equation is valid for all fields, not all constant field, but even for large part of electromagnetic fields. Now, this current, if we call this current conduction current, it's valid always, without any exception, for all fields. Amount of free charges which are moving through any surface per unit time, per unit area, equal gamma times electrical field. Gamma is unit divide rho, resistivity. If I ask you how resistivity changes, what you will tell me? You have to help me, otherwise I'm in a free space. So how resistivity of the rocks changes? Salt, what is resistivity of salt water in Indian Ocean? What is resistivity? Approximately. I would not mind if you make.
Less than 1 meter?
Less than 1 meter. Okay, very good. Maybe smaller? What about 0.1 ohmmeter, 0.2 ohmmeter? Is it satisfactory? Now, let us do together one job. Let us take tank with water. So remember, we finished with curl and divergence. Now, so water. If it's a distillated water, you can buy somewhere. What is the resistivity of this water? How large? If it's a pure distillated water, what would be resistivity or conductivity of this water? 10 power, maybe 10^8. Huh? Suppose there is no, what causes conductivity? Free ions. So if there is no ions, no conductivity. Now I start to pour salt. Naturally, conductivity starts to. Now I increase 100 ohmmeters. What is the resistivity of the water which we drink here? What I know in Colorado around 30 ohmmeters. What is the water in Perth?
10 ohmmeters in the hotel.
So around. Now I continue to pour salt. What would happen with conductivity of the water? How long? How long? So very soon you start to see salt on the bottom. It's an interesting question. What would be the lowest approximately resistivity of the water in normal conditions when temperature 20 degrees Celsius? What would be the resistivity? Around. Can I make 10 minus 4 ohmmeters, 10 minus 3 ohmmeters, 10 minus 5? Huh?
10 minus 3, minus 2.
If we succeed 5 times 0.05, we would be lucky. So it's interesting. Resistivity changes. Resistivity changes from infinity to 0.05 approximately. Now, that's electronic conductivity, correct? Ionic, I'm sorry, due to ions. Now, how to make conductivity higher? What material you suggest to increase conductivity? Metals. So amazing gap. Amazing. What is the conductivity of metals?
Minus 6.
Conductivity, minus or plus? Plus. So 10.7. So you see what is going on. Salt water from resistivity from infinity to around 0.05. Then very long nothing. And then suddenly only metals. 10.6, 10.7. Is there some material which has intermediate conductivity? Do you know what is it? I'm checking your geological knowledge, not. Sorry? Clay? Just a moment. Just a moment. We will come back to clay. No, I'm asking between 0.05 resistivity and 10 minus 6, 10 minus 7. Is there somewhere material which has very high, very low resistivity, but it's much greater than resistivity of metals? Huh? Ceramic? Are you sure? Huh? I asking about material which we can find as geophysicists. Sorry? Oh, graphite. Finally we got it. Yes, graphite. It's a 10 resistivity, 10 minus 4, 10 minus 5. So that's range of change. Clear? Now, since we discuss Ohm's law, let us continue a little. Tell me, please, how do you feel from physical point of view? What kind of parameters very important, which affects conductivity? So we are going to physical properties. We have to, because it's a physical law. Now, tell me please, do you agree that higher density of ions, the stronger, the greater conductivity? Huh? So in materials where higher density, it will be stronger. What else would affect? If iron is very lazy, it does not want to move, how it will affect conductivity? Because remember, Ohm's law is the bridge between two completely different fields. It's a force field, electrical. That's movement of charges. For given electrical field, it's important density of charges, very important. But there is another factor. What is the factor? I almost told you. Mobility. So, not too bad to tell yourself, conductivity is the sum, density of positive charges times their mobility plus density of negative charges times mobility negative ions. So it's not too bad to feel what does this coefficient proportionality means. Now, we have to finish. 1 minute more and then we finish. When we will start again? After lunch. After 40 minutes. Okay, let us stop here. We will continue next time. You have to watch for me. Yes, very good.